In a previous video, we saw how to find the volume of a solid of revolution when the region that we were revolving around the axis of revolution was shaded against it throughout the interval. In this example, we're looking at finding the volume of a solid of revolution using something called the washer method. Now here it says to find the volume of the solid of revolution formed when the region f of x equal the square root of x plus 2, x equal negative 1, x equals 7, y equal 1 is revolved about the x-axis. So I started by graphing the different equations involved in bounding the region. So f of x equal the square root of x plus 2 is this graph. X equal negative 1 is a vertical line at x equal negative 1. X equals 7 is a vertical line at x equals 7. And y equal 1 is a horizontal line here. And then I'm revolving it about the x-axis. So if I take and I shade in the region that we're interested in spinning about the x-axis, I want to envision what sort of a picture or what sort of a 3D object I would get from that. Now notice this x-axis is my axis of revolution, and the region that I'm revolving around the x-axis is not tight against it, it's up away from it for all or part of the interval. Well, if we think about what happens with that, think about possibly having this apple. Now if I took this apple and I actually core out the middle of it, and I think about then having that being my solid of revolution and this being my axis, notice that the axis of revolution would go through where you have void between the region that was spun around to make this. So if I take slices that are perpendicular to the axis of revolution, then I'm going to get a slice that is a washer. And some of these are off a little bit. Let me look at one that's better. Here we go, like a washer. So this is named a washer method because it's like the washers that you put on a screw when you're screwing that in to put some things together. So washer method is when you have still that short height, a cylinder, but you've cored out the middle. In order to find this volume, you want to think about having the overall volume of to the outside so coming from your axis of revolution to what would be the furthest reach away from the axis of revolution. So for here, from the x-axis, it would be reaching out to the curve the square root of x plus 2. And that volume of that then would be the integral from negative 1 to 7 of your, remember it's pi r squared h to find the volume of each of those little slices of the cylinders. So I have the pi, and the r is the outside radius. So that's the square root of x plus 2 squared. And then how tall each of those little slices that we took are vertical subrectangles, so that's your dx. But that gives me the entire thing, the apple before it was cored. So I need to subtract off of it the volume of that core part that we took away. And that's minus the volume, so pi, times the integral from negative 1 to 7 of the radius from the axis of revolution to the inside part of what's being revolved around. And in this case, it's giving me a radius of 1. So when we write this out in general, our overall volume with this is pi times the integral from a to b of capital R of x squared dx minus pi times the integral from a to b of small case r of x squared dx. So you're taking the outside volume and you're coring out the inside volume. And there are some common factors here that we can factor out and then use our properties of definite integrals. And a lot of times you'll see this as pi times the integral from a to b of capital R of x squared minus small case r of x squared and then dx. And again, it's dx when we're taking our subrectangles vertical, like we're doing in this case as we slice across. So let's get back to the specific one that we're working. It's pi times the integral from -1 to 7. Square root of x plus 2 squared is x plus 2 dx minus pi times the integral from -1 to 7 of 1 dx. Integrating, we have the integral of x is 1/2 x squared. The integral of 2 is 2x. And we'll evaluate that from -1 to 7. And then minus pi times the integral of 1 dx is x. Again, evaluate that from -1 to 7. So we're going to plug in the 7 minus plug in the -1. 2 pi cubic units. So that's an example when we're using the washer method. The region that we're spinning around an axis is not tight against the region, and we're taking our subrectangles perpendicular thinness-wise to the axis that we're spinning around, and that we would do then the washer method. If you're looking at this and having it revolving it around the y-axis, and so you're going to take your horizontal subrectangles, then you would have a similar equation only with dy and capital R of y squared minus small case r of y squared. And the other thing I wanted to mention was the reason we did do the dx for this is because when I looked at this region as I was going from left to right, I had consistency of a specific curve on the top and the other curve on the bottom, and it was already solved for y equal the square root of x plus 2 and y equal 1. So it was easy to go ahead and do that and easy to find our antiderivatives for it over that span.